Video, we are to draw the shear force in the bending moments diagram for a simply supported beam with a varying distributed load. And in this case, the load is a triangular load. So first of all, we need to calculate the support reactions to help us to draw the shear force in the bending moment diagram. So we'll make use of our equilibrium equations. So we'll take moment about A. So sum of moments about A should be equal to 0. And we are taking clockwise moments as positive. So this whole triangular load is going to cause a clockwise moment. Because it's clockwise, it's going to be positive. But to get the moment, it should be the force times the distance. And to get the force of this triangular load, we need to find the area of this triangle. So to find the area, it's going to be half of the base of the triangle, which is 6, times the height, which is 3. So this area of the triangle has given us the force. And we know that the force will always act at the centroid of that figure. So it will act at the centroid of the triangle. So let's say this is the position of the centroid of the triangle. So from here to the straight side of the triangle is 1/3 of the base. And from the centroid to the slanted side of the triangle is 2/3 of the base. So we know that this times base times height, the area of the triangle is the force. And the force is acting at the centroid of the triangle. So because you are taking moment about A, we need a perpendicular distance from the centroid of the triangle to where we are taking the moment, which is A. So this means that you are going to use 1/3. Perpendicular distance is going to be 1/3 of the base. And the base is 6. So this is the clockwise moment the triangular load is going to cause. So that's clockwise. VB will cause an anti-clockwise moment, so it will be minus VB times the perpendicular distance, which is 6. So these are the only forces causing moments, and we equate it to 0. So we'll make VB the subject. So let's send 6VB to the right side. 6VB So when we solve this, we are going to get 18. So to find VB, we'll divide through by 6. So finally, VB is equal to 3 kilonewton. Now let's find VA. To find VA, we need to sum vertical forces. And let's take upward forces to be positive. VA is moving up, so it's going to be VA plus VB is also moving up. So VB, the whole triangular load is moving down, so it's going to be minus. And to find the force, we are summing vertical forces. So to find the force, it means find the area of the triangle. And this is going to give us half of the base, which is 6, times the height, which is 3. So these are the vertical forces. Then we equate it to 0. So let's make VA the subject. VB is equal to VA is equal to, when we solve this, I'm going to get and move it to the other side, I get 9. So 9 minus VB. VA is equal to 9 minus, we already know VB to be 3. So 3. And this is going to give us 6 kilonewton. So we have to find the horizontal reaction. So sum of forces in the horizontal direction is equal to 0. So forces moving to the right should be positive. So HA is positive because it's moving to the right side. We equate it to 0 because there is no other horizontal force. And these are the support reactions. So now we can go ahead and calculate the shear force. So the shear force. So shear force at A, we'll calculate two shear forces. So shear force at A prime is equal to 0. Then shear force at A is equal to 0. Then we'll pick the previous one, so 0. Then we'll factor the force, the vertical force acting at A, which is VA. So 0 plus VA, because VA is moving up. This is going to be 0 plus VA. So VA is 6, and this is going to give us 6 kilonewton. Good. Now we can divide the span into two, and we'll locate a point at the middle and call it C. What we want to do now is that we want to calculate for the shear force at C. So this means we have made a cut at C, and we are taking our left side to calculate the shear force. So shear force at C, because there's a varying distributed load, we only calculate for only one value for the shear force. So shear force at C is equal to the previous one, which is 6. But there's a load here before you get to C. So we need to factor this load. We need to put it into consideration. So it's coming down. So it's going to be negative. So 6 minus. Now we need to find the area of this figure. So this is a trapezium. Or you can divide it into two like this, so that you get a triangle at the top. Then you get a rectangle below. And you find the area of the triangle, then you add it to the area of the rectangle. But I'll be using the area of the trapezium. So the area of the trapezium is half multiplying the sum of parallel sides times the perpendicular height. So the sum of the parallel sides, so these are the parallel sides of the trapezium, this side and this portion are the parallel sides of the trapezium. And the perpendicular height is this. So the perpendicular height is going to be 3 meters because it's at the middle. We're calculating for the shear force at the midspan. So the area of the trapezium, so we know that this side is 3, but we don't know this side. But because it's acting at the middle, we can say that it's 1.5 kilonewton per meter. To prove it, you can use similar triangles. So 3, this side of the bigger triangle, divided by this side of the bigger triangle, which is 6, is equal to this portion, which is 3. So, in this portion, which we don't know, so you can use a variable x. After solving, you are going to get 1.5. So the area of the trapezium is half of the sum of the parallel sides. So this is going to give us 3 plus 1.5. So 3 plus 1.5 times the perpendicular height. The perpendicular height is going to be 3. So this will give us the area of the trapezium, and that's all that we need. So the area will give us the force. Good. So when we solve this, we're going to get 6 minus 6.75, and this is going to give us negative 0.75 kilonewton, and that's the shear force at C. So now we'll calculate for the shear force at B, but we'll calculate for two values for the shear force at B. So shear force at B prime is equal to negative 0.75, which is the previous one, minus, because we need to factor this part into it. So this part is a triangle, and to find the force here, we need to find the area of the triangle. So it's going to be negative 0.75 minus half of the base of the triangle. So the base is 3 times the height. The height is 1.5. So this will give us the force. When we solve this, we're going to get negative 0.75 minus 2.25. And this will give us negative 3 kilonewton. And now the shear force at B. Shear force at B is going to be negative 3 negative 3, which is the previous one. Then we'll factor in the vertical force acting at B. So this is going to be negative 3 plus 3. So plus VB because it's moving up. So plus 3. VB is 3. And this will send us to 0. So this is the calculation for the shear force. Now the shear force diagram. The shear force at A prime is 0. Shear force at A is 6. So 6 kilonewton. And connect the two. Shear force at C is negative 0.5. So let's say negative 0.75 kilonewton. Okay, so let's say it's like somewhere here. Then shear force at B is 0. Sorry, negative 3. B prime is negative 3. So negative 3 somewhere here. Then shear force at somewhere here. And shear force at B is 0. But because the load that we have is a triangular load, we are going to connect the points using a parabolic curve. So the nature of the parabolic curve will be like this, and it's going to decrease. And it will decrease up to this point. So let's say this part is the 3, negative 3 kilonewton. Okay, then we'll connect these two. So this is a parabolic curve. When you look at the triangular load, you will see that it is decreasing. The parabolic curve is also going to decrease to this point. So this side is positive and this side is negative. So this is the shear force diagram. Now let's move on to the calculation for the bending moment. So the bending moment. So BM bending moment. So the bending moment at A, I'm taking moment to my left. So I'll call this BME. So it's moving in the anti-clockwise direction. So it's going to be minus BME. So that's the only moment there. So negative BME is equal to 0. And I divide through by negative 1. I'm still going to get BME to be 0. And now a bending moment at C. So bending moment at C, I'll choose to take my right because it's easier compared to taking my left. When I take my right, I'll call this bending moment at C. So it's moving in the clockwise direction. Bending moment at C is positive. So be a positive BMC. VB is going to cause a moment. The value for VB is 3 kilonewton. So that means anti-clockwise moment. So minus 3 times the perpendicular distance to where I'm taking the moment, and that's 3. This triangular load, the reason why I took my right is because I'll get a triangle here, but when I take my left, I'm going to get a trapezium and it will be complex. So the triangle, I need to find the force. It is causing a clockwise moment, so it's going to be plus half of the base, which is 3. The force is the area, half of the base, which is 3 times the height, which is 1.5. So this is giving me the force times the perpendicular distance, and that will be the centroid. So the centroid to where I'm taking the moment. So I'm moving to the straight side, and it is 1/3. It's going to be 1/3 of the base. The base is 3, so 1/3 of 3. Everything here is equal to 0. So bending moment at C is equal to, when I send this here, I'm going to get 9 minus, so I'm going to get 2.25, and this will give me 6.75 kilonewton, 18 meter. Now bending moment at B, I can choose to take my right. So bending moment at B. Because I'm taking my right, I'm taking moment to my right. So B and B. So clockwise positive is equal to 0 because there's nothing here. So now I have to draw the bending moment diagram. A and C and B. So A is 0, B is 0, then C. So C is 6.75 kilonewton meter. Because it's a triangular load, I'm going to connect the points using a cubic curve. So it's going to move like this and like this, and it's all positive. So this is the bending moments diagram, and this is the shear force diagram. Thank you for watching this video.